In the previous video we went through chapter 5.1, and that was the beginning of our introduction to waves. We saw the wave basics. Now we will continue from chapter 5.2, the behavior of waves. Under this chapter we have several subchapters, and in this video we will discuss this subchapter 5.2.1, wave phase and superposition. By the end of this section you should be able to understand what is meant by terms wave front, superposition and phase. In the O-level or IGCSE classes you would have already learnt about wave front, but what about superposition and phase? You would not have really learnt about superposition and phase in the O-level or IGCSE classes, so we will see them here in the A-level class or IAS class. Explain examples of wave superposition. What is superposition? What is phase? Let's see. So you can see the first thing is phase here. We have wave fronts. Always remember these wave fronts are perpendicular to the ray. The green line can represent a ray, R-A-Y, and the wave fronts, which are shown by these black lines, are always perpendicular to the ray. You have to remember that. Then we have wave superposition. So basically there are three topics here, and also we have superposition of continuous waves. Now what is this superposition of continuous waves? Superposition, first we will see that. You can see what happens here when the two waves superpose. We get this wave here. Here when these two waves superpose, we get this. This is called constructive interference. From the name itself you can figure it out. The other one is called destructive interference. You see here the amplitude is 0. Here the amplitude is maximum. So therefore this is called constructive, this is called destructive interference. Now see, the two waves interfere. That's why we say interference. And that's the last part of that. By the way, these definitions are very important. Make sure you memorize them with understanding, because in the exam paper they can ask you to write down these definitions. And if you try to write in your own words, that's fine, as long as you don't miss certain keywords that the examiners are looking for to award you the full marks. We have wave fronts are lines connecting points on the wave that are at exactly the same phase position. So for example, if you look at the crest of a wave, so you join all the points along the top of the crest of the wave, that is, we can say, a wave front. Then if you do that for all the all the crests, so there will be a distance of one wavelength between them. So another thing you can remember is, if you have two adjacent wave fronts, the distance between them is equal to one wavelength. From here to here, that's one wavelength. Now you have learned what is a wave front. They are lines connecting points on the wave that are exactly at the same phase position. But we didn't learn this yet. For now you can try to understand the definitions. Constructive interference is the superposition effect of two waves that are in phase, producing a larger amplitude resultant wave. So you see, it's like a construct. They get together, and the amplitude here is double the amplitude of one of them if they both have the same amplitude. Destructive interference is the superposition effect of two waves that are out of phase, producing a small amplitude resultant wave. Here you can see the two waves have the same amplitude. That's why when the crest and the trough meet, the amplitude is 0. Here you can see it has a positive amplitude, here a negative amplitude. So when these 2 points combine, it will be 0. The amplitude will be 0. Okay, let's go back to the beginning. Phase. All points in a wave will be at some position through their cycle of oscillation. Okay, so we already saw in the previous chapter how we can form a wave. I saw I explained that we can form waves in a slinky, and there is also a video. If you go to my channel, you can see a video where I'm creating longitudinal waves as well as transverse waves in a slinky. So what happens then? The particles oscillate when the waves move in the material. So for example, in the slinky, the wave can move along the slinky. We can produce a longitudinal wave, and when the wave moves, it creates vibrations. All points in a wave will be at some position through their cycle of oscillation. Some of these positions in the cycle have their own names, such as peak or crest. Okay, so if you have a water wave, for example, okay, imagine this is like the shape of a water wave. So these top parts are called the crests. The bottom parts are called the troughs. So even if you look at this wave here, these top parts are called crests. They have a positive amplitude, we can say. Then the others are called the top parts are called crests. The bottom parts are called troughs. Troughs have a negative amplitude. Yeah, such as peak or crest, trough. Compression or rarefaction. In the previous video we saw the compressions and rarefactions. We have compressions and rarefactions in a longitudinal wave. So in the longitudinal wave, remember, where the particles were close together is where we have a compression. Where the particles are further apart is where we have a rarefaction. The remaining points through a cycle are important, but there are too many to give them all names. We describe any position through a cycle by a number referring to as the phase. A complete cycle is considered to be equivalent to rotating a complete circle. So the phase position will be an angle measurement, where a complete cycle is equivalent to 360 degrees. So you can see, if you go along this, here it's 90 degrees. From here to here, the angle is 180 degrees, 270, 360. Phase angle. So in a wave also, you can think this position 0. Here the angle is 90, 180. Now see how it corresponds to this. When it completes quarter of a circle, this is the circle. We start here. Remember, we measure the angle anti-clockwise, and that is positive when you measure the angle anti-clockwise. You would have learned this for O-level mathematics or IGCSE mathematics. So from here to here, the angle is 90 degrees. From here all the way to here, the angle is 180 degrees. From here all the way around to here, that is 270 degrees. Then one full round is 360 degrees. Now compare that with the graph. So from here to here it's 90. See, from here to here it's 90. From here to here it's 180. See, all the way up to there. Then we go 3/4 of the way. So 1, 2, 3/4, that is 270 degrees. We go one full round, that is 360 degrees. So the phase angle when it goes one full round is 360 degrees. Wave phase represents the position through a complete cycle measured in angle units. It is quite common to measure phase in the alternative angle units of radians. We have degree unit and also we have the radian unit, where one complete cycle is 2 pi radians. If you go all the way around, that is 2 pi radians. Table A shows common phase positions in the two equivalent angle units, along with the fraction of a complete wavelength that they represent. As waves are by definition a repetitive cyclic process, phases of more than 360 degrees could be reduced to their equivalent value within a first cycle. For example, the peak after 1.25 cycles has exactly the same phase as the wave in the first cycle. So its phase could be quoted as either 450 degrees or 90 degrees. Now let's see. So if you go from here all the way to here, that's 360 degrees. 360 plus 90 is 450. So you see, you came to the same position. So let's say this is the position 90 degrees. If you go all the way around here and complete the angle there, so that is 360 plus 90, which is 450. 450 degrees. That's what they mean here. Has exactly the same phase as the wave peak in the first cycle. So its phase could be quoted as either 450 degrees or 90 degrees. Now 90 degrees in radians is pi over 2. What you can remember is pi radians is equal to 180 degrees. Pi radians is equal to 180 degrees. So half of this is 90 degrees. Half of this is pi divided by 2. So 90 degrees is equivalent to pi divided by 2 radians. That's how you can do this unit conversion. You can remember this and then convert from degrees to radians or radians to degrees. So 5 pi over 2, that is 450 degrees. Now 450 degrees is 360 plus 90. Similarly, since we go all around here, so from here to here it is 2 pi plus pi over 4. 2 pi plus pi over 4, then that will give you 5 pi over 2. You can do the addition, okay? 2 pi plus pi over 2. Then you should get this 2 pi plus pi over 2. And you can see they have given start of the cycle, phase is 0, angle is in degrees here, then phase in radians, that is also 0, number of wavelength 0, because when we are here, you see the angle here, phase angle is 0, you can see the angle is 0, then that's the start. Wavelength is 0, number of wavelengths also 0. Quarter of a cycle, phase is 90 degrees, in radians it's pi over 2, the number of wavelengths is pi over 4, quarter of a wavelength. So when you go from here to here, you can see the angle is 90 degrees and the whole cycle is from here to here, which is 360 degrees. So 90 degrees is quarter of this whole thing. So from here to here, the angle is 360 degrees. From here to here, you can see it's quarter of the full wave, quarter of the cycle. That's why it's 90 degrees. Or we call it quarter of a wavelength, because from 0 to 360, from here to here, we can say it's one wavelength. Okay, so from here to here, it's quarter of a wavelength. Quarter of a wavelength. So we can say in terms of wavelength also. By the way, path difference is always given in terms of wavelength. Phase difference is given in terms of angle. So from here to here, that will be half a wavelength, 180 degrees. From here to here, that is 3/4 of a wavelength. Phase angles in degrees and radians and also compared to wavelength. See, one whole cycle is 360 degrees, or in radians it's 2 pi radians, and in number of wavelengths, that's one whole wave, right? So the wavelength is one whole wavelength. Okay, then what about wave fronts? I already explained. if you join the points on a wave that are all in phase, then we get the wave front. Diagrams of waves are often drawn as lines, as in figure B, where all the points on a line represent points on the wave that are at exactly the same phase position, perhaps a wave crest. Okay, if you take the top of the wave crest, then you can join all the lines along that particular crest, top of the particular crest, and you do the same one for the next crest, and then you will have two wave fronts. The distance between those two wave fronts is one wavelength, perhaps a wave crest. These lines are called wave fronts. They are how the sea might look observed from a helicopter, where the troughs are in shadow and so appear dark. Waves are traveling in this direction. The direction the waves travel also we can say is the direction of the ray. Wave front, all points on a wave peak where phase is equal to 90 degrees. Okay. Then from here to here, the difference in the phase is again 90 degrees. From here to here it's one wavelength, right? Okay. Oh no, from here to here that phase difference is 360 degrees, not 90, because you join the points along the crest of one wave, and then again you join the points along the crest of the next wave. So this from here to here, that's one wavelength, okay, which is 360 degrees. Between wave fronts, the phase difference is 360 degrees. The path difference is lambda over 2. All points in each wave black lines are in the same phase position, 90 degrees or pi over 2. The green line shows direction of travel is called a ray. Green line showing the direction of travel is called a ray. So I already explained that rays must be perpendicular to wave fronts. So you can see clearly they have also stated that. So now you know about wave fronts, and also you know about the phase angle in degrees and radians, and also compared to wavelengths. So this table can be figured out if you understand how to convert from degrees to radians, radians to degrees, and in this case how much of a wavelength that is. Wave front, wave superposition. When waves meet, so each wave will carry to cause a wave displacement at the point of intersection according to its phase at that location. The net effect is that the overall displacement will be the vector sum of the displacements caused by the individual waves. After the encounter, each wave will continue past each other. So let's say we have this wave going to the right, this wave going to the left, and what will happen? There will be constructive interference and destructive interference when the waves move. Now there is actually an animation for this. I'm going to show you that as well, then you can understand this better, what is superposition and how to do calculations, drawings to show the superposition, superpose the resulting wave due to the superposition of the individual waves when they meet or when they interfere. Okay, so here is some explanation. After the encounter, each wave will continue past each other as the energy progresses in the same direction it was originally traveling. This can be most simply illustrated if we consider just wave pulses passing each other as in figure C. When waves meet, the displacements would add to each other to give the overall displacement for each location. And you can see the example here to understand it better. So you have two transverse waves moving towards each other. Now when they overlap, say for example here they just overlapped or they simply interfered, the resultant wave, the wave that you get when the two combine, is having an amplitude that is the sum of the individual amplitudes or displacements of these. Okay, we can say displacement because amplitude is the maximum displacement, but this is not having maximum displacement everywhere. You understand, it's a transverse wave, so if it's a wave, yeah, it can't suddenly have all the same amplitude everywhere. Right, this is what we have. So this wave and this wave, they overlap, then where they meet we can measure the distance to there, then the resultant wave will be twice that. See, it's also explained here. Now what happens, this wave moves to the left, this wave moves to the right. Now what happens, the one is fully overlapped with the other. So what will happen, the amplitude of the resultant wave is amplitude of A plus amplitude of B. It's A plus B. Then over here what happens, this is moving to the left, this is moving to the right. Yes, so again they simply go through them, see, go through each other, and again it's even though they interfered, once they pass they just continue as they were continuing before. Wave pulse displacements add when they meet in the same location. If the wave pulses in figure D are traveling on the surface of water, then they would be trying to displace the water molecules upwards briefly as it passes. When both meet at the same location, the wave A lifts the water a little. You can refer the diagram. And then pulse B is also lifting up, so the water raises even higher to the level of two displacements added together. This effect is thought to explain the tales from returning sailors that they saw a sudden freak wave which then vanished as quickly as it appeared. The sum of the many waves traveling in many different directions which happen to coincide at a point at one instant could cause a huge instantaneous displacement which then drops again as the waves continue on their way. So here you can see, because they interfered, this will have a very high amplitude which is the sum of the individual amplitudes. Then again they continue after overlapping, they continue as they used to continue. The sum of many waves traveling in many different directions which happen to coincide at a point at one instant could cause a huge instantaneous displacement which then drops again as the waves continue on their way. See, surface elevation, time. Multiple small waves coinciding in the same location can lead to a brief, very large displacement. This graph of sea surface height is of sea surface height at Drabna North Sea oil platform on 1st January 1995, showing a freak 18-meter wave. Two waves meet, the displacement could add to each other to give the overall displacement for each location. Superposition of continuous waves. Okay, I think this part is now clear. Superposition of continuous waves. We saw that previously in the previous page also. This here you see, and also this here is a superposition. When they overlap, the resulting wave will have the sum of the displacements or amplitudes of the waves that interfered to produce that wave with constructive and destructive interference. if rather than a single point along the path of the wave, we consider waves superposing over an extended space, the outcome is a continuous wave, that is the sum of the displacements over time in each location. I will try to show you an animation to help you understand this better. If the two waves are in phase, their effect will be produced a larger amplitude resultant wave. This is known as constructive interference. I already explained that. If identical waves meet and are exactly out of phase, if their phase difference is 180 degrees or pi radians, then the resultant is a zero amplitude wave. See, it's also shown here, constructive and destructive interference. Okay, meet and out of phase here. Destructive interference, zero amplitude. Okay, this idea of complete destructive interference can be confusing. Imagine shining two beams of light to the same place, and at the point you see blackness. In right circumstances, as explained in section 5.2.4, this is exactly what happens. So we will see those afterwards. Now we are in 5.2.1. It is important to know the phase difference between two waves in order to determine what will happen as a result of their superposition. Waves that constructively interfere, as with the top pair in figure F, this you see here, must be in phase, which means they have a phase difference of 0, because the waves are going together. As phase repeats every complete cycle, this could also be said to be a phase difference of 360 degrees or 2 pi radians. Okay, so you can answer these questions. Now let me go into a bit more detail on this. And the next one is 5.2.2. So let's go through 5.2.1. Alright, so let's go through an animation of this where you have constructive and destructive interference when waves interfere. Now, I'm going to use this website to show you what's happening. So let's start. Now you can see this is a rope, and in this rope we are creating a wave. So you can move the wave, you can move the rope up and down, and then you get this wave. Now let's see. It will be incident on this surface. Here it's tied, so the rope is not moving from one place to another place. It's the parts of the rope that are moving. Now see, interference occurred. So in blue you have the reflected wave, in red you have the incident wave. Okay, so let's see what happens. See, I can pause it like this. Now you can see the blue wave, that is the reflected wave. The reflected wave is moving to the left, incident is wave, which is in red, is moving to the right. So now you have constructive and destructive interference. See, the blue wave is the reflected wave, the red wave is the incident wave, and what you see in black is the resultant wave. Okay, now you see here, both of them, the red wave and the blue wave, red wave means the incident wave and blue is the reflected wave, when they interfere we have superposition. So right now, exactly here where the trough and the trough meet and the crest meet, then you have, if they both have the same amplitude from the beginning, then you have the resultant wave, which is the sum of the amplitudes of the individual waves. That will give you the displacement, or the amplitude in this case. So the amplitude of this will be 2 times the amplitude of that. Okay, let's resume. And same thing with the displacement. So where they are, where one is positive, the other one is negative, so you can see where you add the two. Maybe here it's plus 5. Here it's minus 2, so it will be plus 3 then. 5 plus 5 minus 2 is plus 3. So the amplitude here will be plus 3. You see how the standing wave is formed by these two waves. Okay, now you can see the process is complete. It has gone, strike the wall, and then it's coming back as a reflected wave. So it's continuing like this. So this is to help you understand superposition. Now I will pause it maybe somewhere. I will show you where we have destructive interference. Now see what is happening. See, in slow motion now. The black wave is the resultant wave. It is due to superposition of the individual waves. So the red wave is moving to the right. Sorry, blue wave is moving to the red wave is moving to the right, blue wave is moving to the left. You can see what happens. See, now they are moving apart. One is moving to the left, other one is moving to the right. Okay, in this instant, let's say what happens. So for example, if you take this point, so you have to look at it in the vertical direction, here and here. So you can see that this is maybe minus 5 for example, then this would be plus 2 for example. So then the displacement of this in the vertical direction will be minus 3. Here minus 5, here plus 2, so minus 3. Okay, let's go to the next one. Okay, so we just completed this part, but I also have created a note on this. So let me quickly go through the note. By the way, this information is normally available to only the paid online students, but just for this bit I will show this to you. All these notes can be downloaded once you purchase the complete online course for IAS Edexcel Physics. It's also available for both IAS and IAL. If you want to purchase only the IAS course, then you can have access to all the IAS notes. The link to purchase it is in the video description. You also have my WhatsApp number there or Instagram that you can use to contact me if you have any queries regarding purchasing the course. So let's go through this. 5.2.1 wave phase and superposition. This is what we saw. So remember, when you complete 90 degrees here, that's quarter of the wave. So that also we can say is equivalent to quarter of the wave. Let me just save this and I can zoom it. Okay, so I have got it here. Now you see I can zoom it. Alright, so here we can see this. I think image is much clearer as well. Okay, if I zoom in a bit more, you can see this. See, 90 degrees, that is quarter of a wavelength. So if you consider this to be the full wave, the full wavelength, so from here to here 360 degrees, that is also 2 pi radians. You can see the values are given here, 360 degrees, 2 pi radians, and that's one whole wavelength. So half of that, quarter of that, you can figure it out from this table here by looking at this. And you can also see this here. We remember we measure the angle anti-clockwise from the positive x-axis. So I have given the unit conversion, the conversion factor pi radians is 180 degrees. So 180 degrees is equivalent to pi radians. And then we saw the principle of superposition. The principle of superposition, it's here. When two or more waves meet at a point, the resultant displacement is the algebraic sum of the displacements of the individual waves. So we have the green wave and the blue wave. When they interfere, the resultant wave is the red. 1. Adding two waves by the principle of superposition. The red line is the resultant wave. So what you can do is you can even measure this. So if this is let's say 2 centimeters, from here to here it's 3 centimeters, then 2 plus 3 is 5. That means from here to here it will be 5. Let's look at another part of the resultant wave. So here to here, from the x-axis to the top of along this vertical line to where it meets the green wave, let's say it's plus 4, for example. From here to here it's plus 4. Then from here to here, the blue wave, the displacement is, let's say, minus 3, plus 4, minus 3. Then this will be plus 1. Okay, so that's how you figure out the displacement of the resultant wave. And these definitions are important. I already went through them. So let's go back to this. So I think I have covered everything here. Make sure you answer these questions and check the answers for these questions. They are available also in the course. We also saw this ray and wave fronts perpendicular to each other. The distance between distance between wave fronts is 1 wavelength. I already explained all that. Also you can see this from this book. This is the Cambridge book. So these blue lines are wave fronts. You can see the distance between two adjacent wave fronts is 1 wavelength. The blue line with an arrow we can say is a ray, it's perpendicular to the wave fronts. Here you have diffraction. We will see those later. This is called a ripple tank. We can use this to create waves in water. Okay, diffraction. Okay, so that's the end of that first video in chapter 5.2, which was chapter 5.2.1, and in the next video we will go through chapter 5.2.2, which is stationary waves.